So I will tell you one of our last research here, and also make many comments about research, youthful research career, etc. So what you see here, and I invite comments from my friends from Turkey here, you see here some lists which you cannot read probably. Can anybody read these things? Barely. Okuyabiliyor musunuz bunları? No. So this is there are 8 groups here of music. I'm a physics professor, don't forget, but there are 8 groups of music here. And these are Turkish music, and this is Western music. Here is arabesque, and there is the first, and there are 10 artists here. Bergen is a very important, now deceased actor, singer in Turkey. Has anybody heard of Bergen here? Bergen. Yes, you have. Yes, and then there is, in here, if we go further down, there is Ibrahim Tatlıses. Has anybody heard of Ibrahim Tatlıses? Yes, if we go further down, there's Kibariye, Müslüm Gürses, Müslüm Baba, Orhan Gencebay, etc. Then there's Turkish rap. Turkish rap here, there's Ceza, Ezbel, Esel, Kajmer. Has anybody heard of those? And then there's Uzi here, and there's Turkish pop, which of course with Tarkan, with Yaşar, with Demet Akalın, etc. And down here there's Turkish classical, Hicaz Ud Taksimi, Kürdi Ud Taksimi, Muhayyer Kanun Taksimi, etc. This is Turkish classical music. There are 10 pieces here. Here there's Western music, and again I'm not going to go through every one of them, but blues, there's B.B. King, jazz, there's Duke Ellington and other people. Western pop, there's Adele and other people. And there's Western classical, including Beethoven, Brahms, Grieg, etc. So all of these points are, there are 80 different pieces here, grouped in groups of 10 here, Turkish and Western. All of these things are a point in here. So we have done a spin glass chaos analysis, which I will tell you about, the way a statistical mechanician does on this, me and my students, and we have been able to put each one of these in everything here. There are 80 points, and these are the various types here that you can see here. So we had a lot of fun doing this. We listened to a lot of music, and you're going to see other versions of that. Now, this is a part of the same work. My wife, Bedia, Professor Bedia Berker, tells me nobody will understand this, but we all understand, right? This is the top of a head. This is the nose. This is the 2 ears. And these are different points on the skull. And you put electrodes there, and you take electroencephalograms. You measure the electric current in the brain from these different points. And basically, they are from this point in here. And from these measurements, you get these points here. And again, this is, we analyze this using spin glasses and chaos. By the way, at any time, you can ask me questions, ask me to repeat what I'm saying. You can say I'm speaking too fast. I can repeat it anyway. And if you don't ask me questions, soon I'm going to die because I cannot breathe when I speak so fast. So please do ask me questions. Okay, so now we continue here. How did all of this came? And this is actually a physics paper you can see here. Let's go here. I'm going to go back now and tell you about the things that we work on as a statistical mechanicians. So, and if you take an ordinary magnet and you do a microscopic model, at each point on a lattice there's a spin which is plus or minus 1, and these are a sum over nearest neighbors, and this is a constant. Now, this, if J is positive, this is the energy of the system. If J is positive, the lowest energy state is with everybody aligned up or everybody aligned down. This is called ferromagnetic alignment. If J is negative, the lowest energy state is up, down, or down, up, down, up, down, up. This does not have to be a magnet. It could be a lattice system where +1 means there's a particle, 0 means there's no particle, or it could be an alloy, alaşım, where there's type A or type B atoms, or it could be the brain. In our brain, there are cells called neurons, and neurons can be in 2 states like this. Either a voltage passes through them or a voltage doesn't, 2 states, and they interact with their neighbors. So basically, this is the very general model here that everybody studies, and it has been studied for a long time, over 50 years, And it's an important model. It has a phase transition, it has a critical point, it has divergences, critical singularities, and there have been probably dozens of PhD theses out of these. But even more important is if I take this J and put it inside here, and I make it randomly, frozen randomly, plus positive or negative. In that case, this is called a spin glass, and there's and it's found in materials, in various systems, which I will tell you about. There's an important new effect here, which we call frustration, in Turkish bunalım, that's how we translated it, in which, let's say that the blue one is in a locality, the blue bonds are with positive and the red ones are with negative. This spin tells its neighbor to align in this way, this tells its neighbor to align this way. This one doesn't know who to make happy. So it has to choose one. The choice it makes here affects a choice in another center of frustration. The whole system is very complicated. Now, to find the lowest energy state here took us 5 seconds. To find the lowest energy state here, if you find it in closed form, you immediately get a Nobel Prize, or you get the Fields Medal of Mathematics, or both. It probably cannot be done. There's approximate and numerical studies to even find the lowest energy state of this. And this is the models that we work on. Now, let me go back here, and how do we solve systems like this, which have a critical point, which have a phase transition? A phase transition is a catastrophe. Suddenly, I mean, if you take a material, you change the temperature, things are going to change slowly. But suddenly, if there's a phase transition, suddenly something is going to boil, or something is going to change catastrophically. So that's why it's a hard problem, a phase transition. So now, the way we study it here is like this. It's a hard problem, but in 1971, a young physicist named Ken Wilson introduced this theory, which said, don't solve it all at once, solve it gradually. How do you solve it gradually? You take, in the system, you take 9 spins, and you assign a leader to them. You take 9 spins here, you assign a leader to them, and you look at the interaction. From the interactions between the spins, you write the interactions between the leaders in a calculational way. So you get a new effective temperature based on this. So, and then you take groups of leaders, and you have a super leader, etc. And step by step, you solve the whole system, and this is called renormalization group theory. Now, in fact, if you're in the high temperature phase, if you're right here, the T prime is going to be here, here, here. You're going to go to T equals infinite. If the temperature is infinite, KT, the energy scale is infinite. So the difference between energy levels is negligible compared to infinite KT. So the system is disordered. All microstates are equally likely. On the other hand, if you flow down here where T goes to 0, in that case, all the energy differences become important compared to KT. So there's one of them, the most important one, is going to survive, and the system is going to order. And in between, there's an unstable fixed point where, by doing analysis, you can calculate the experimental quantities, such as critical exponents, TC, etc. Now, Ken Wilson, here a few comments. Ken Wilson is now defunct, rahmetli, but he is someone that I met, older than me, of course. He, one generation older than me, Professor Weiss. He came up with this theory in 1971 when he was 35 years old. And this is so important that he was rewarded. How? Everybody thinks about Nobel Prizes. You shouldn't think too much about it. But Nobel Prizes are somewhat political. They give them in 3 different places. And they also wait till you have one foot in the grave so that you don't enjoy it. Here, at least one person understood my joke. If you laugh at my jokes, I'll tell more of them. If you don't, I won't tell any. Okay, so here, Ken Wilson got the Nobel Prize in 1982, which means he was 46 years old, quite young, none of the feet in the grave, and alone. So that shows how important this was. And now, what happened, again, Ken Wilson is someone I knew. What happened to Ken Wilson after Nobel Prize alone at age 46, that's a different story, which I won't tell now. But anyway, this is an important theory. So, but you can see here that there is in these systems where there is no frustration, there is a continuous flow in this direction or in this direction. Now, we have in ourselves discovered something with my student, Suzanne McKay, in 1982, where if you solve a spin glass system, meaning if you solve a system, one of these systems, instead of a continuous flow, you get chaos. At every different scale, you get the temperature which becomes strong, weak, in a chaotic sequence. That's a complete new discovery, and now it's accepted as the basis of a spin glass system. So if I go here, there are many pictures here, we'll look at one of them. This is the density of frustration. For one level of frustration, instead of going to a fixed point like this or here, the system goes back, and this is temperature, the tangent of 1 over temperature. The system goes chaotically back and forth here. It measures in a chaotic way. It samples all points here. If you look here, this is the scale transformations you have here, and this is the tangent of the inverse temperature. You see it's chaotic here. Now, this is a recent work with Alpar Türkoğlu, my student, published in 2020. And there we've even made this model more interesting, where we changed the local degrees of freedom from being +1 to -1, from being A, B, C, D, E, F, G. We increase the local degrees of freedom. So if you increase the local degrees of freedom, you escape. So increase local degrees of freedom, and you escape from chaos. This is almost a political message. But we did find this in our work. So now, in fact, there are models that we constructed in which we can do these exact solutions. So that's how we come here, in which we can basically, this thing here is a chaotic sequence, but it has a structure to it. Music has a structure to it. The brain signals have a structure to it. Music, there's one note that keeps repeating itself, or an assembly of notes, and those are connected. You can connect those with each other. Now here, before that I should say this, I'm walking around here in 2 dimensions. There is something in front of me, behind me, on one side, this side. I'm in 2 dimensions. If I was also looking at top and down, I would be in 3 dimensions. But in systems like this, there's one node, and it's connected to another node, it's connected to another node, and these have something called fractal dimensions, which are not integer. And in fact, there is a whole spectrum, combination of different dimensions inside of a chaotic data, complex data like this. So we can do a numerical analysis and get the distribution of dimensions, distribution of connections in something chaotic like this. We can do that for our models, and we can do that for music. But our models, we can change them any way we want, and we can match music. So we have a way of classifying different pieces of music. So this is a general classification scheme for all complex phenomena that we have discovered here. So now let me tell you how we do this. In here, this is spin glass data. This is dimensions, and this is the strength of dimensions. Think about it that way. These are all calculations. And these are the models that we have created called hierarchical models, which you can solve exactly. And this is the inverse temperature that you get. So doing here, we get these dimensions, the red ones, with different strengths here. To that, there's also, analyzing music, we get these points in here, and we have to make these things close to this one by changing the model in here. But those of you who did experiment, if you have a set of data points, another set of data points, it's very hard to get them close together. It's easy to fit a point to a curve. So what we do here is we take the spin glass, we do a fit here, and then we see how close we are to the music data, and then we change the model, and we change this to get as close as we want between this curve and these blue points, and these are the red points and these points. So we make the best fit that we can, and then we have classified our music. So in here, this is, for those of you who are experimenters, this is R is the goodness of the fit. If that's 1, it's a perfect fit. And in here you can see the points. My wife, Professor Nihat Berker, is some of my friends there know her, is an experimental chemist. And she says that, well, if you have an experimental fit that is 0.99, well, it's not good enough to sell your mother, but it's good enough to sell your husband, she says. So we are in dangerous territory here. This is very good fits. So now, as you can see for these music pieces, we have different parameters here, PB and M1, and we can classify them and see whether they cluster together. We can look at different complex data and see whether they fall together. Oh, this is our general model. There are parameters here, PB, P, M1, M2, PB, PC. And this is for various cross-sections here as a function of PB and M1. These red points are where you have chaos. And you can see that here. There's a crescent and a star here, right? And there is no chaos there. I can also say that. I say it in the publication, actually. There is no chaos in the crescent of the star, but all the other red places we have chaos. So now we find ourselves, we fit this chaos to the music pieces, and this is what we find for the various genres, the various types of music. We have, for various cross-sections, we have these 80 points. Now in here, we discover something important, that there are 88 different types of music. They are all intermixed. They have all influenced each other, with one exception. Can anybody tell me is there some systematic clustering here that you can see? If you tell me there's a special price, I will sing a song for you. Nobody's going to say that. They don't want to hear that. Okay, in fact, while you think about it, about telling jokes, when I was giving classes at MIT, every week, in every class, I gave a quiz. And it's very hard to prepare a quiz. I mean, if it's too hard, the students don't like it. If it's too easy, they say you're insulting us. So you have to prepare the right amount. And one day with my MIT students, I just couldn't prepare the quiz. Half an hour to the class, 20 minutes to the class, I'm sweating. I just couldn't prepare it. So I went to class, and this was a very kind of a sour class. They were very serious. They all think they're geniuses. They're not smiling, etc. And something happened, and they laughed a little bit. So I made a mistake that I said, since you're laughing at my jokes, I will not have a quiz today. But that was a mistake. After that, every time I opened my mouth in every class, they started laughing just to get out of the exam. But anyway, so you should watch out what you're saying. In the meantime, you find, is there a clustering that you see here? A systematic clustering. It's hard to see. Let me tell you, maybe you were saying something. What is it again? Here? Well, you see that more there, you're right. The clustering that you see, there's a clustering between Western jazz and Western classical. They occur together. Everything else is mixed. So that's a finding. So it's a finding where everything is mixed. That's important. How can you find, arabesque music with here Ibrahim Tatlıses and Beethoven and Brahms are all together? If I tell him that, he would be very happy. Otherwise, Western jazz and Western classic is also mixed. Now, if you look at the brain, something here, you see a real clustering. If you take signals from the back of the brain, these are these signals here, the C points, and you can see there are three types of signals: music listening, resting eyes open, resting eyes closed. Music listening is clearly away from the other ones in a telltale cluster. And the other ones, there's also some systematics here, but you can see we have a way of systematically taking complex things and being able to separate them. And this suddenly became very famous. Every field wanted to work on this. So first of all, we got this paper, which is in referee now, with my 3 students. I will tell more about them later on from various places. We'll come back to that. Now, and there's another the piece that we're working on. I will not show the details. Governance and COVID cases, deaths in 180 different countries. Spingler's chaos, complicity, and classification. We're working there with İzzet Darendere, who's an associate professor in California State University, also an adjunct professor at my school at Kadir Has University. But now I continue more on the brain. The dean of medicine from Bahçeşehir University, Turkic, is a long-time friend of mine, found this, and here there are signals from various pieces of the brain and how they fall. This analysis has not been done completely yet. It's being working. Here's another one, another brain work with my good friend Kamil Uğurbil from Minnesota, and a colleague, a postdoc of his, and our group. And again, this is data, currents from the brain and how they fall, various parts of the brain. Kamil is a very close friend of mine. He's a classmate of mine from high school. So we went to the same high school. And he's a professor, he's a triple professor in Minnesota. He's a professor of chemistry, radiology, and medicine. And he may get a Nobel Prize, he should get the Nobel Prize. He's the first person who measured brain currents in human brain in the 1970s, late 70s. So he may get a Nobel Prize, he deserves one. Here's a little bit more on Kamil. This is us in my high school. All boys high school. There's almost none of them left now in Turkey. Now, can you see me here, anybody? Which one? I am here somewhere. Where am I? Here. Where am I? Somewhere? No, it's not Istanbul Erkek Lisesi. No, I'm not asking what the school is. Can you see me here? Yeah, so here I am. And this is Kamil, but he's making the peace sign signal, right? Nothing else. But now, this is in 1964, before your parents were born. This is now Kamil, he's imperator. He's like Fatih Terim now. He's right there. And he, of course, he deserves a Nobel Prize. So you should keep track of your friends, and it comes to good use. So now we're doing also work with music from Bahçeşehir University, and this is different types of sound music and how the analysis is going. This is all ongoing work. And then I will talk a little bit about my students. Students are very important, both when you're a student and when you become a young faculty member. You don't have to become a professor. When you are an assistant professor, doktor, öğretim üyesi, having students is very important. And nowadays, the days are past where, like my father was a mathematician, you go in a little ivory tower, you work by yourself, Now you work with students. They keep you alive, they keep you energetic. So in my first student I took when I became a postdoc at Harvard, and there were 12 postdocs in Bert Halperin's group, and I was the only one who had students, and I'm the only one who got immediately a job at MIT afterwards. This was in 1977, and I had always have students, and since even when I was president of Sabancı University. So in here, currently in my group, I have 10 students, and I'm trying to increase them to 20. I will, I think. So this, and from all places, for example, at Kadir Has University, we have courses open to the public. And there, one of those courses, Phase Transitions and Renormalization Group, this is a course I developed at MIT. John R. took it. He was a top student, and I asked him to work with me. Now he's a PhD student at Kadir Has University. He has 4 different published articles, and we still keep working together. However, we also work with, nowadays students yourselves are very good, much better than us, and you start being very good at a young age. So we have at Kadir Has University a summer school for high school students and a winter school for high school students, 2 weeks with each one of them. 2 2-week periods in summer, 1 2-week period in winter. And there we have about 1,500 students coming, taking 25 different classes. And there I give 4 different classes. I give augmented mechanics, augmented electricity and magnetism, quantum mechanics, and phase transition and renormalization group theory. Now, these students, Alpar Türkoğlu, in 2017 was the top student in augmented mechanics. And I asked him to work with me. And again, when you become assistant professors, you should go to the students, to their feet. Sometimes they're shy. And now you should go to the professors and ask them whether I can do work with you. If they say no, they say no. Okay, but that's no problem. You have to ask. Then Ibrahim Keçoğlu, my other student, was in 2018 as a high school student. He was a high school student here. He was a high school student here. And he was a top student in the Introduction to Quantum Mechanics. I asked him to work with me, and he did work with me. And this is basically our classes. This is the summer schools. No, this is the winter school. There are 21 different classes. There are 24 different classes here. The ones that are in purple here are the classes that I teach. So in here, for example, in the summer school, my classes are twice as long as anybody else's, and there are 4 of them. Usually people share these. So basically, I do 8 times more work than the other professors, but working hard is good. You feel better, and you're successful. Being successful is good. So you have to work hard. You have to enjoy, of course, what you're doing, and then you shouldn't stop. There is no such thing, too much of a good thing. So you should work hard, and here in the winter school, I have 2 classes, 4 times more than anybody else. But these students have been #1 here. So I have always wanted to publish it. At MIT, we have, back when I was a professor there, I was a professor between 79 and 99. Undergraduate students always did research. Now also at MIT, and there's, what's the small school next to MIT? There's a small school, starts with an H. Harvard. I shouldn't say this because both of my sons are at Harvard. My older one is a professor there. My younger one is graduating now. And they both started doing research from day #1. So you should start doing research. And if it doesn't work, you go to somebody else. But that's because your generation is very good. But now, high school students are also very good. So from our summer and winter schools for high school students, we take on students to do research. As you can see, I've always wanted, so I have many papers from MIT in which the authors are undergraduate students, lisans öğrenci. But you start working with a high school student, and by the time you publish, they become a university student. So you don't show their high school addresses. That I did for the first time this year. Here is a Yağız Devre. We finished this. He was a top student at the summer school for high school students. We finished this and got accepted by the referees, which is another battle that you give, while he was still in high school, Üsküdar American Academy in Üsküdar. And then there's going to be more now. And as soon as he published this, he was accepted to Caltech, Columbia, Princeton, etc. So that's not too bad. Oh, that means I stop. Okay, suddenly alarm sign. I didn't look at the time, but so let me give you a little bit more about, working hard is fun. You can start it when you're very young, younger than me. At Istanbul Technical University, you all do research as an undergraduate. I know that, my friends from there. So you should start working hard, you start young. Why? Being successful is good. It makes you feel good. You're good at everything. You're good at your personal relations. You're good at sports. If you are also good at the work that you do. Nowadays, our work defines us in a very large way. So then suddenly, in March 2020, what happened? What happened in March 2020? COVID happened. So suddenly, here I am giving 4 courses every semester. And suddenly we were shut down. So what did I do? I had a whiteboard delivered to my home, and I started doing 1 lecture every day for all 4 courses. These are my courses, my phase transition renormalization group theory courses. These are my videos of every lecture here, 25 videos, and I have a fun 26th one. And every time I change topics, I change a T-shirt here. You can see that color of you have to make life fun. And these classes are on my webpage, free. You can download them. They are in Turkish, but you can freely download them from my webpage here. This is the phase transition classes. Then I went to my other classes, and in total, by the time the pandemic was finished, I had all 4 classes on my webpage, 126 different lectures. And you can freely download them. Everybody downloads them. It has been looked at in thousands. This is phase transitions and renormalization group theory. This goes on. This is augmented mechanics. And in here, we go here. And in here, for example, there's a lecture called Kedi insan at fil zıplar mı? Can anybody translate this to English? Lecture number 24. Yes? It says, kedi, insan, at, fil zıplar mı? Yeah? Can they jump? So this is a thing about where a cat, a human being, a horse, and an elephant, do they jump? Actually, using basic mechanics, will prove that there's a 20,000 between a cat and an elephant. There is a 20,000-fold mass difference, but they all jump to the same height. And in this lecture, using basic mechanics, you can prove that they all jump to the same height. In fact, I had given this as an exam problem in one of my exams 20 years ago, and half of the class did it actually. So you should try to prove that, why all these animals jump to the same height, and you can then, there's another such problem, which I will tell you now, that you have does anybody know what Hamsi is? Does anybody know what Hamsi is? I have a friend from Azerbaijan here. You should know what Hamsi is, no? Hamsi is a fish in the Black Sea. It's a Turkish, well, it doesn't carry a flag, but it is so Hamsi is a fish that we eat a lot from the Black Sea. And it's not sturgeon, it doesn't give caviar, I'm sorry, but it's a fish. Why? It's a small fish like this. Why does Hamsi, and this is another quiz question, why does a whale or a dolphin, big fish, and Hamsi, they basically, they can swim at the same velocity? A dolphin is much bigger, Hamsi is much small. Why do they swim at the same velocity? That's another quiz question. They have to swim at the same velocity because dolphins eat Hamsi, so they have to be able to catch them, but some of the Hamsi have to be able to escape. So it's all kind of the fact that you can, again, using basic mechanics, you can prove that. Anyways, two problems for you. I continue here. This is electric and augmented electricity and magnetism. Magnetism, all on the web for freely here. And here, I'm almost at the end here. We do all of this work internationally at Kadir Has University. And here, I have to thank the people who have founded. It's a foundation university. It's non-profit. It's a private university if you can, but it's non-profit. And in here, there is the Rahmetli defunct Mr. Kadir Has, who gave all of his fortune to the university. And now he passed away, but his sons, Can Has and Nuri Has, are supporting this kind of a scientific push very strongly. And this is my president, Sondan Durukanoğlu Feiz. She in the summer school for high school students. She teaches brain science. Here we are before the pandemic, but we still laugh now. So this is if you want to ask any questions, if you want to download these things, this is my web address at Kadir Has University. This is my web address at MIT, and these are my emails, and this is my cell phone. You can call me anytime. Everybody calls me. I answer all my phone calls. So that is it. I didn't look at the time. We did quite well. So I'm done. Thank you very much. But I will take questions.